Greetings to everyone. Today we are going to discuss the oxidations by using reagents like DDQ and selenium dioxide. DDQ and selenium dioxide are reagents which are useful for oxidation at active CH functions. Now let us see the first one, DDQ. DDQ, DDQ means it is 2,3-dichloro 2,3-dichloro 5,6-dicyano-1,4 benzoquinone. This is a structure of benzoquinone, and here it is numbering starts from here 1, 2, 3, 4, 5, and 6. So at the 2 and 3 positions, you can see two chlorines are there. So this is 2,3-dichloro. At the 5 and 6 positions, we have two cyanide groups. Okay, we call this as cyano 5,6-dicyan. And at the 1 and 4, you can see this is the benzoquinone positions. Okay. So this is the total molecule is abbreviated as DDQ. Okay. And if you use the stretching frequencies of C double bond O, in DDQ it is around 1650 centimeter inverse. In the C triple bond N it is 2220 centimeter inverse. Whereas the C double bond C in benzoquinone skeleton it is 1550 centimeter inverse. Now 2,3-dichloro-5,6-dicyano-1,4 benzoquinone, which is abbreviated as DDQ. So it is a chemical reagent with the molecular formula C8Cl2N2O2. This oxidant is useful for the dehydrogenation of alcohol. Dehydrogenation means removal of hydrogens and phenols and steroid ketones in organic chemistry. DDQ decomposes in water, but it is stable in aqueous mineral acids. Coming to the stability of DDQ, DDQ can react with water and it can give off hydrogen cyanide HCl, which is highly toxic. So it should be stored in very dry area. So at a low temperature and weakly acidic environment will increases the stability of DDQ for the storage. Now, coming to the some of the important features of DDQ. DDQ is electron deficient because you can see it in the molecule. You have all the benzene skeleton in this case, the benzenite benzoquinone skeleton. It is in this case. It is attached with C double bond. It is an electron with the drying group. Chlorine it is a moderate electron with the drying group. Cyanide it is a strong electron with the drying group. So we can say this molecule is electron deficient due to the presence of these many electron withdrawing substituents. So since it is electron deficient, this can take electron excess species. That means it is having the ability to attract towards, to show attraction towards electron excess species like H minus hydride ion. So here in this case, suppose if you have any allylic CH, from that allylic CH, DDQ can abstract H minus. Since it is electron deficient, it can take hydrogen in the form of H minus. Then whatever the formed allyl carbocation, this gets stabilized. So that means this CH in this case is an active CH. And here in this case, benzylic CH. From the benzylic CH also DDQ can abstract H minus hydride ion. And benzyl carbocations are formed, which are also stable. So allyl CH functions and benzyl CH functions generally referred as active CH functions in this case, because the so formed intermediates in this case, that is allyl carbocation and benzyl carbocations, are stable. Okay. And DDQ cannot abstract hydrogen in the form of hydride either from ethane or simple cyclohexane because they do not possess active CH function. So DDQ abstracts hydride ion H minus from benzylic and allylic position. Therefore, for DDQ, oxidation reactant must be with the reactant must be with the allylic and benzylic CH functionality. For example, if you see this molecule, it is a cyclic skeleton. Okay, it is a cyclohexene. This cyclohexene here you have a double bond, and with respect to this double bond, this position and this position will become allylic CH positions. Okay. Now DDQ, due to its high electron deficiency, it can abstract H minus from this allylic position, and H minus goes and attaches to this oxygen. Then this carbon oxygen bond pair of electrons are shifted over here, and this carbon carbon double bond pair of electrons are shifted here, and then this carbon oxygen bond pair of electrons are shifted onto the oxygen. And you can see allyl carbocation is formed in this case. And here in this case you can see the DDQ is converted into a oxide in this case. Okay, this oxide again abstract hydrogen from the alpha allylic carbocationic position. Okay, so now here hydrogen is abstracted in the form of proton H plus, since here how you have O minus oxide state in this case. Okay, now this abstracts hydrogen. So one of the hydrogen is abstracted by H minus, H abstracted as H minus hydrogen. Another hydrogen is abstracted as H plus. But the initial reaction is started by the abstraction of H minus hydrogen ion. So due to that one, okay, the molecule is highly electron deficient. The reaction initiated by the transfer of H minus from this allylic position towards the DDQ. So this molecule is an electron deficient. Now here in this case you can see the both oxygens in this case are in the form of phenolic state. Okay. Now whatever the molecule you have got in this case, here in this case this is a, here in this case you can say this is an oxidation type of reaction, because you have removed hydrogens, two hydrogens from one hydrogen from this position, another hydrogen from this position, and you got a double bond. Okay, so this is oxidation. So for one double bond formation, how many DDQ is required in this case? One DDQ is required. For example, if you want to have oxidation in this position is becoming allylic position to this one, and this position becomes allylic position to this one. So at any one of the positions, you can have oxidation with the next equivalent of DDQ. So for removal of one H2, okay. So how many DDQ is required? One DDQ is required. Therefore, one equivalent of DDQ is required for one double bond formation. For example, let us take a molecule tetraline. Okay, so tetraline, this in presence of DDQ and solvent benzene, when you undergo for a reflux, this molecule, it will give you naphthalene with the reduction of DDQ into phenolic skeleton. Now, if you see the reaction criteria, how the reaction will take place, and what are the key features you have to observe while a reaction is performing. Here in this case, when DDQ is added into the reaction mixture, DDQ forms a charge transfer complex with benzene, due to which what happens, the solution, the reaction solution, it uh, it gets a red color formation. Okay, so now when the reaction is actually started or the reaction is in progress, the DDQ gets reduced into phenolic skeleton, and the reduced form in this case, while the reaction, when the reaction is in progress, the red color turns into yellow because the reduced form of DDQ is in yellow color. So how we can observe the reaction progress means, if the red color is turning into yellow color, that means the DDQ is getting reduced. While the DDQ is getting reduced, what is happening? The reactant is getting oxidized. Is it clear? The DDQ is a oxidizing reagent. It itself undergoes reduction and it oxidizes another reactant. Is it clear? So the change in color during chemical reaction indicates oxidation of reactant by DDQ. So whatever the reduced DDQ which is formed in the reaction mixture, it can be separated. Okay, the byproduct which is formed, the phenolic byproduct which is formed, it can be separated by treating with an aqueous alkali, which is in the form of salt. It gets separated. Now let us see the mechanism how DDQ is converting tetraline to naphthalene. So as we have seen in the previous example, this position, it is benzylic and we have a benzylic CH. So H minus hydrogen transferred from benzylic CH to the DD. Now you get a benzyl carbocation. From alpha position to the benzyl carbocation, the CH, whatever the hydrogen in this case, it is transferred as a proton towards the oxide of this DDQ. Now, this both the, already one of the oxygen is converted as OH, another O minus it is converting as OH. So one of the DDQ is reduced. Okay, and you got one double bond here in this case. This is the one double bond. Now next, another DDQ comes into action, another equivalent of DDQ. Now this abstracts hydrogen in the form of hydrogen from this benzylic position. Then the benzyl carbocation formed in this case. And this is the partially reduced DDQ in the form of oxide. and the oxide abstracts proton from this allyl benzyl carbo alpha position of benzyl carbo cation or alpha position of allyl molecule, allyl skeleton. Now, after the abstraction of hydrogen in the form of proton, you get this reduced molecule of DDQ again. So you get another double bond in this case, which is called as naphthalene. Tetraline is converted into naphthalene. So here you got two double bonds and one DDQ and another DDQ. Two DDQ are utilized. So for every one double bond formation, one equivalent of DDQ is required.